Hi everybody, if there was a competition for the greatest sorting algorithm of all time, Timsort will be very high up on the list. In this video, we'll find out what makes Timsort so exceptional and how it works in sorting data that we throw at it. The main thing to think about is when it comes to the sorting algorithms, especially the ones that we've seen so far, none of them are perfect because how quickly they run is very dependent on the kind of data our algorithm is being asked to sort. And so let's take a look at this table. Here we have the average time, best time, and worst time for the kinds of sorting algorithms we've seen so far: quicksort, merge sort, bubble sort, selection sort, insertion, counting, and radix. Now, what we can see here is that on average, these algorithms work as the way they're advertised. Quicksort, big O of n log n. Selection sort, big O of n squared, and so on. But the thing is, when you look at the worst time for some of these algorithms, the behavior changes dramatically. Quicksort normally runs at big O of n log n, really fast, great algorithm in general. But if the input it's being asked to sort is fully in reverse and our pivot selection is having an off day, quicksort can run as slow as big O of n squared. That's almost as slow as one of our slowest sorting algorithms that we have. On the flip side, if the input that we're asked to sort happens to be fully in sorted order, so we're asking you to sort a sorted set of values, insertion sort runs at a speed of big O of n, linear time. And so what we see is that there's variability in how well our sorting algorithms behave, and this variability is caused by or determined entirely by what kind of input it's being asked to sort, which means that slow sorting algorithms can run really fast. Fast sorting algorithms could run really slow. This is, from a theoretical point of view and from an academic point of view, great. Sometimes you have bad days, sometimes you have good days. But in real world situations though, you want to have a predictable environment where your application will never slow down to a crawl because of some kind of input that you didn't anticipate being thrown at it. You want to have a consistently good experience, especially when it comes to sorting. So what if you could avoid the speculation and choose the right sorting algorithm based on what exactly our unsorted data is doing? That is really where the concept we want to talk about here, hybrid sorting algorithms, really come in, because a hybrid sorting algorithm takes advantage of the strength of multiple sorting algorithms and creates what I like to call a super algorithm. And what this means is this: because we're relying on multiple sorting algorithms under the covers, in a hybrid sorting algorithm, the worst case behavior of any kind of a situation is minimized, because if we detect a certain use case that an algorithm is really poorly designed for, we swap that algorithm for a better one on the fly based on what our data is doing. And this allows us to have a situation where no matter what kind of data we throw at it, our sorting algorithm under the covers adapts and does the right thing. That's really the core of a hybrid sorting algorithm. Now, before I go deeper into this, if you'd like to learn more about hybrid sorting algorithms or just data structures and algorithms in general, my best-selling book on this topic, Algorithms: Absolute Beginner's Guide, is just what you need. You can find it online bookstores and in physical bookstores as well. So links to all of that below. Getting back to it. One of the best hybrid sorting algorithms, the most popular one, is Timsort. And the way Timsort works is that it combines the best features of two other sorting algorithms. It combines the merging logic of merge sort and the typical sorting logic of insertion sort. And the key idea behind Timsort is to take advantage of the existing order in the data, take advantage of data that is partially sorted and has more combinations of things that are more sorted than less sorted, because in the real world, no data we'll ever encounter will often be truly random. There'll be moments in the data where things are growing sequentially or decreasing sequentially, and these natural orders in the data are ones that Timsort is specifically optimized to run really quickly on. So the way Timsort works, and we can grossly oversimplify it by looking at these three steps. First, it divides the data into small chunks, and these chunks are known as runs, R-U-N-S, runs, like you're walking, you're running, runs. The second step is to sort these chunks using insertion sort, and the third step is to merge these sorted chunks using a smart merging strategy, typically found in merge sort. Now, we're going to look at an example to kind of put all of this into a more understandable picture. So here's the collection of unsorted values that we have. And for this example, I'm going to use a lot of values to highlight how insertion sort works, because it's the best way to make sense of it. And of course, if you're watching it, you're probably like squinting, going, I can't see these numbers. I see unsorted values, I see a lot of boxes, but this is just hard to read. So what I'm going to do is, just for visualization purposes, have that long collection of numbers broken up into 3 rows, as you can see here, and this is the arrangement of it. I broke it up, but the actual values themselves all follow sequentially. Now, the first thing we do in Timsort is we take our data and we divide it into what are known as runs, what I called chunks earlier on runs. And the size of a run usually varies, but it's usually between 32 and 64 items. Because of explaining how it needs to work, having 32 items on the screen would be a little too much data for you to see. I'm going to use a run size of 4. And so what we're doing here is dividing our entire collection into sequences where you have run sizes of 4 items in each, except for the last item, which of course has 2 items in it, which is okay because not everything's going to be a perfect division of 4. So the first thing we do after we divided up our full input into runs is we sort them, and we sort them sequentially. So the first run is sorted. In this case, it was 4, 12, 35. It was sorted to 0, 4, 12, and 35. And this sorting is done by using insertion sort. And I'll talk a little bit more about that in a moment, because you're probably wondering, is an insertion sort a terribly inefficient algorithm for doing any kind of sorting? And so we keep sorting. We sorted the first run, then we sort the second run, and we keep repeating this process until every run has been sorted. The detail to note, though, is that each individual run is sorted. In aggregate, our collection of data is still not sorted, because each individual run needs to be, could be larger or smaller than the next run next to it, and the values in it could also be larger or smaller as well. And that's where our next step comes in, where we merge the runs. The final step is for to take our individually sorted runs and merge them into larger and larger sorted runs, where the end result will be we merge 2 runs together, and the second to last step, and the final step, we have one gigantic run, which is basically our full collection, now in sorted order. And the way the sorting works is that we sort adjacent runs. We'll talk more about that as well in a few moments. So if I color code the adjacent runs, you can see the first 2 runs are blue, the second 2 are purple, the next 2 are in a beige yellow color, and then the last 2 are in a pinkish color. So, and the way we merge them is by using a merge sort like logic, where we compare each value, which one goes first, which one goes second. The combined version of it, though, will have a fully sorted selection. So when we do this combination, you can see after first round of merging, our 2 runs in each cases have been merged together, and now we have fewer runs, and we keep repeating this process until we have no more runs left. So now we have, in this case, 1, 2, 3, 4 runs. We're going to do one more merging operation of the adjacent runs again. Now we have 2 runs. You can see that now what we had many runs before, we now are down to just 2 runs. This is also our final step. So we merge them one more time. And when we do that, you can now see that all of our runs are properly sorted into one gigantic run, which ironically also happens to be our unsorted input, now in sorted form. So now we have a fully sorted set of values. Now, if you're looking at this and you're probably wondering, wait, all we did was run insertion sort, which runs at a speed of big O of n squared, and we're just doing the merging operation of merge sort, which is probably order of like worst case n log n, but probably more the log n or linear size of things. How is that in any way an optimization or faster? If anything, if I'm thinking through this, it's probably like n squared of log n, which is not very fast at all. And this is where the optimizations come in, because there's a sticker speed of Timsort, which is what we saw right now. Then there's the actual insider speed, for those of us in the know, on how Timsort can actually be much faster than we've seen so far. And that's where we have these optimizations that come into place. And these optimizations revolve around detecting common patterns in our data and customizing the various steps to account for how the data is structured. We talked about earlier how Timsort is optimized for real-world data. We're going to see now how those optimizations in real-world data actually end up kicking in. So the first thing we do is that we know that insertion sort is horrifically slow when the data it's dealing with is in reverse order. And that's when the worst case running performance for it happens. So to avoid this, when we're running Timsort, the algorithm tries to identify runs that are strictly in reverse or descending order and do an in-place reverse on them first before attempting to sort and merge them, which means that there's no sorting happening until all the reversed values are in the more ascending upward line. So for example, let's say we have a set of numbers 4, 8, 13, 9, 6, 3, 21, 53, and 11. And you can also see my cat Pixel is sitting on my lap right now. He's very eager to see how this all gonna play out. So we break this collection of 9 values into 3 runs: 4, 8, 13, 9, 6, 3, 21, 53, and 11. Now notice that when we look at run 2, the 9, 6, and 3, those 3 values are strictly in descending order. So instead of running insertion sort on it, we do a very fast in-place reverse, which now means that 963 becomes 369. And now we run insertion sort on these 3 numbers where the values are now going to be, in this case, 4, 8, 13, and whenever a cat is ready to have a recording video, you can see some stuff happening that is not predicted. So he kind of moved the slide too early. So you can see now after we reverse the runs, we now have a sequence of numbers that are not strictly ascending, but they're not strictly descending. And so we can run insertion sort and have much better performance than big O of n squared you typically see with it. So this is one optimization, being able to detect runs that are in the worst case reverse scenario and reversing them to be ascending or going positive. The second one is that this is probably the one that Timsort is most known for, and that's galloping mode. Galloping as in horses that are running and going really quickly. And it has a more technical term that is binary search insertion. And this is a technique used by Timsort during the merging phase. And it's designed to handle cases where a run has many elements that are already in their final sorted position relative to the other run. And here's what this means. So during merging, if Timsort notices that many consecutive elements from one run are being chosen, it means that those values are probably already in their sorted location. It switches to galloping mode, where it stops the merging. It actually, instead of comparing elements one by one, it jumps or gallops over multiple elements to see where all the elements should ultimately find themselves in. And this means that we're reducing the number of comparisons, often by a significant number when merging runs, especially ones that are partially sorted. And this example will make that a little bit more clear. So here are the 2 runs we're merging. 1, 2, 3, 4, 5, 31, 48 are the values in run A. 10, 11, 12, 14, 16, 17, 18 are the values in run B. Now, when we start this merging operation, what we will do is it will compare the first item, run A, the first item in run A, 1, to run B. Is 1 less than 10? It is. So we move that to our final merged collection. Is number 2, the second item in run A, is 2 smaller than 10? It is. Is 3 smaller than 10? It is. 4 and 5, all the first 5 digits are all less than the very first value of run B, which means that we can safely add them to the merged collection. Now, at this point, the next value we're going to be getting into is 31. And the question is 31 smaller than 10? It's not. Is 31 smaller than 11? Nope, it's not again. And we keep asking ourselves, where's the best place to place 31? At this moment, what's going to happen is that we're going to switch into galloping mode and look at this and say, it seems like a lot of the values here are already in their final sorted position. Is it worth doing a comparison and asking each one whether we want to be in the right spot or not? At this point, since all elements in run B are smaller than the 5th element in run A, than 31, Timsort, instead of doing anything extra to make sure that we do a comparison on each one, we add all of them at once to the merged collection. So instead of doing 1, 2, 3, 4, 5, 6, 7 extra comparisons, we may do one comparison, kind of this peek ahead to see how the numbers go, and then we just add them all at once in one fell swoop, which means that we saved a lot of comparison time being able to do this. And the last device I put at 31 and 48, those will just be added automatically towards the end of what we're doing. So by using galloping mode, Timsort is able to speed up the merging process by quickly adding multiple consecutive elements from one run when it's clear that they're all smaller or larger than the next element in the other run. And notice that because we run insertion sort earlier, all the items in the run are already sorted. So you can be confident to know that if the starting number is less, the last number is much larger than what I'm trying to do. All the items in between are going to be sorted fit nicely in between. So this reduces the overall number of comparisons and the sorting time as well. And it's especially great when you're merging runs whose sizes are significantly different. The next optimization that Timsort uses is known as adaptive merging. The merging strategy isn't one where just two adjacent items are just merged arbitrarily. The order can vary based on the sizes of the runs, because the goal is to maintain balance among the runs and avoid really having one single run that is so large that it makes the final merge costly. When you have lopsided merges where one item is much larger than the other when you're trying to merge with, you do a lot of unnecessary comparisons and it just gets really messy, so you don't want to do that. And so here's an example. We have run A, run B, run C, and run D. The actual values in them don't really matter. What is important though is the size of the runs themselves. So run A has, 7 items. Run B has 5 items, C has 2, and D has 3 items. In this case, with adaptive merging, what we're going to find out is it's going to merge the two smallest runs together, because then it makes the subsequent runs and subsequent merging much more efficient. So run C and D we merged, and so now what we have is 3 runs that need to be considered for merging: run A, run B, and the merged versions of run C and D, we're just calling just run C and D. And this is a great way of improving the performance as well. The next optimization that you'll often see with Timsort is that when the number of values we're sorting, especially if it's lower than a threshold of usually 32 or 64 items, there's no point in breaking it up into any more smaller chunks and doing some of the sorts. We just run insertion sort directly on that input. Now, that might seem a little counterintuitive. It's like, wait, I'm running, again, big O of n squared. Not great. The thing is that when we look at real world data, when we look at our actual computers and the various CPUs that are designed to sort values, they can do millions and billions, maybe even trillions of calculations a second. Running insertion sort, even at the speed of big O of n squared on 32 items or 64 items, is actually quite ideal. In no way is it going to be noticeable in terms of performance, and you might also avoid having to create intermediate data structures and things like that to take more memory. So when all things said and done, it's actually quite efficient to just run one of the more quicker and easier of sorting algorithms, insertion sort, on them. So when we have a small list of numbers that need to be sorted, none of the Timsort logic we saw about runs and galloping mode optimizations and all these things, none of that come into place. It gets fed to insertion sort, the numbers are sorted, and the values come back. And so when we tie all these optimizations together, we can answer the question, why is Timsort so efficient? It is efficient because it tries to detect patterns in the sorted data and special case sorting behavior accordingly. And the patterns we've seen so far are the natural runs, being able to detect reversed runs, using galloping mode to avoid unnecessary merging work, enforcing minimum run length, insertion sort directly as opposed to doing anything else, performing adaptive merges, and many other optimizations. But these are the big ones that I wanted to call out. Timsort tries to take the most efficient path whenever possible, and we can see that reflected in the performance characteristics. I started off by saying Timsort is probably one of the greatest sorting algorithms of all time, and the reason for it is because of these optimizations that make sure that in the best case scenario, it runs at a speed of linear time, big O of n. In the worst case and average cases, it runs at a speed of big O of n log n. So in this case, we're clamping the worst case scenario at just big O of n log n, and the best case scenario is now set to big O of n, which puts it in a league that's different than all the other sorting items we've seen. Quicksort is on average really fast, but its worst case is big O of n squared. We don't want that. Merge sort is consistently big O of n log n and a great choice in general, but its best case though is not big O of n, it's big O of n log n as well. It's consistently big O of n log n. So with Timsort, we're faster than merge sort as well. And because Timsort works on a variety of data independent of the range of data and things like that, choices like radix sort and counting sort don't really apply too much here either, because they're very special purpose on the range of numbers being within a certain set of values, positive integers and things like that, which limits their usability in many common cases. The space complexity for Timsort, it's always linear, it's always big O of n. It's always the intermediate data structure you may need as part of either sorting your values or being able to merge the values into its final position. So it's always going to be that. And so here's an example just to give you an idea. When you're sorting data that's already there, insertion sort does it all in one pass. When I talk about the best time big O of n, this is an example of it, because you might not have seen my video on insertion sort, and even if you did, it's good to have a refresher. Notice that at no point are we doing multiple passes on the same values, which is where the performance slowdowns happen. And so as we talked about, the performance of Timsort is on par with QuickSort's average performance, but its optimizations give an edge. And even though it says big O of n log n, the optimizations actually make it a faster big O of n log n, because big O kind of glosses away the intermediate details on how fast something is running. In this case, we can be reasonably confident that it's not just a general big O of n log n where it's equivalent in speed to QuickSort. It's likely much faster than QuickSort because of these optimizations that makes any smaller numbers we typically ignore truly small in the speed of how fast Timsort runs. And this is actually, borne out by real-world data. Here's some data from the V8 team in the Chrome team that talks about what is the performance of of Timsort versus QuickSort on data that is partially sorted. The larger numbers are supposed to be better, and the lighter blue is of course Timsort, and the darker blue is QuickSort. You can see that in many cases, Timsort is magnitudes faster than QuickSort, and that's something that you can definitely not gloss away as just like aberrations in the data. This is really significant. It's not just like a few percentage points faster where you're like, I can live with it. It's 15 times faster in the case of decreasing numbers, or 10x faster in random numbers. So highly efficient algorithm. So with that, if you want to learn more about Timsort, the best way is to just go to crypto.com, read my article on Timsort, where I talk about not just how this works, but also implementation of Timsort as well. I take a very popular open source implementation and have it work in the browser so you can see how it works. Just go to Google, type in Timsort and Krupa. You'll find the tutorial very quickly. If you have any questions, ask in the forums. One of the best places to ask, where you can learn not just about algorithms and data structures, but also about other topics you might be interested in as well. So definitely don't feel shy. I'll be happy to answer many of those questions myself when I see them. Lastly, to be notified of more videos that I might be creating in terms of data structures or other topics, hit like, comment, or subscribe to be always on the cutting edge of knowing when these videos come out. Sign up for the newsletter for updates in your inbox on various things I'm talking about. Follow me at Krupa on Twitter, or X as they're calling it, for more bite-sized updates on things that I found interesting on the internet, and also things that I'm posting as well, like to share very quickly. And lastly, I have a lot more books that I write on a bunch of topics. Check them out in the link below, and you'll be able to find those books as well in physical bookstores as well as online bookstores. And with that, I will see you all next time.